Global warming, climate change, whatever you want to call it, the steady rise in the Earth's average annual temperature is a problem that is a major concern for millions of Americans today. Furthermore, it is an undeniable and overwhelming consensus of scientists studying the issue today that this rise in global temperatures is due to the combustion of fossil fuels like natural gas, oil, and coal. And so, people have been turning more and more over the years to green energy alternatives to burning fossil fuels for things like powering their vehicles and heating their homes. While this is happening, we are also in this new and wonderful age where smart devices and the internet have both changed the way we live and offer the possibility to change things farther in the future as they are even further interconnected. We are told that this new technology will enable us to create an Internet of Things that will allow us to control groups of physical objects that can recognize and interact with each other just as packets of information do in the Internet of today. It is my belief that one of the most promising ways such technology will be employed in the future will be in the field of sustainable energy generation, specifically from ocean currents. The idea that I will be describing here, the Seahorse, is an attempt to do just that. But before I begin to actually describe the Seahorse itself, let's take a step back to the discussion about the current state of the climate and how people are trying to burn fewer fossil fuels today. We'll start by taking a look at a couple of the most popular concepts that are currently available to us as a way of extracting power from naturally occurring currents, wind turbines and hydroelectric dams. If we imagine getting a cross-section of a dam and a wind turbine like so, we can see that they basically rely on the idea of building a massive tall structure oriented orthogonally to the ground and then trying to get current to flow around the turbine connected to this structure. They do this in very different ways. The dam blocks the river entirely, storing up its water in a huge reservoir that is used to build up head height for the turbines. The wind turbine, on the other hand, lets most of the current sweep right by its blades and is only capable of extracting a small percentage of the available current passing by. If we look at a pair of tidal generators, we can see that there are some designs, like this here, that are more similar to the wind turbine, and others, such as the one you see now, that are more similar to the hydroelectric dam. But I would argue that all of these designs are silly investments, though the ones trying to generate power from tidal currents are at least closer to what we need. While these ideas might make sense in the future, I will be making the case that there is another way to extract power from natural currents that beats all of these in terms of importance right now, the Seahorse turbine. What makes me so confident? Well, take a look at this pie chart showing where the sustainable, also known as green, energy that is currently making its way onto our power grid comes from. As you can see, hydroelectric power accounts for a larger percentage of the total power added to the grid than wind does. And this is the case even though there is a relatively huge number of wind turbines compared to a relatively tiny number of hydroelectric installations out there. This is because of the massive difference in the density of water versus that of air. Check out this stretch of the North Umpqua River behind my parents' house in Oregon. If I toss a stick in it, we can get an idea of how quickly the current is flowing. It is only flowing at a walking pace. The wind is blowing about that fast, and I can barely feel it. But if I were to try to walk across the river, I would be knocked over and swept downstream before I reached about knee-high in the water. There's a wide disparity between the density of tappable power available in a flow of water compared to a similar current of air. And this is why the hydroelectric installations do so well on the pie chart. The problem with this picture is, of course, that people don't really want to put more stuff into our rivers and streams. So under the current model, it looks like we'll be stuck relying on more of these big wind turbines. And the picture doesn't look too good. I mean, lots of the most promising areas have already been developed, and this is all that we're going to be getting. The same is true for tidal installations as they are currently conceived, though they barely rate mentioning because their contribution is so small. And that really is a shame, because just look at this map of the Earth from the Library of Congress. Just look at how much seawater there is. Now let's look at the Bay of Fundy. According to bayoffundy.net, the tidal current flowing through this bay alone on a daily basis is approximately equal to twice as large as the flow of all the world's rivers combined for the same period. And now let's zoom back out again and realize that on a global scale, the Bay of Fundy is actually quite small. Check out this tidal amplitude or height map made from data collected by satellites scanning the global ocean surface over time. As you can see, the Bay of Fundy gets big tides, no doubt, but it is hardly hogging all of the world's tidal potential. We are talking about orders of magnitude more water in these flows as compared to that in all of the world's rivers combined. So think about all of the issues that you have heard surrounding the construction of conventionally designed hydroelectric dam installations and consider the potential that being able to tap into these flows represents. These are some seriously massive currents of water. Look at this chart showing the average speed of tidal currents in spring and neap tides in the English Channel. It is kind of hard to get information from, but the numbers with 2 digits on either side of the comma are the average speed in knots of the spring and neap tidal currents, respectively, multiplied by 10. So look at one of the numbers, Take the two sets of numbers and separate them, then divide by 10 to get the spring and neap tidal current speeds and knots. This channel is a couple of 100 miles long. I mean, just look at that. Those speeds are as high as you might find in a large, powerful river. The amount of power there is incredible. So the tidal currents you see here, or the ones flowing through the Bay of Fundy, are much larger than the flow of the world's biggest rivers, and that is impressive for sure. But even these tidal flows are themselves dwarfed by the largest ocean currents. According to Wikipedia, the Antarctic Circumpolar Current is the biggest of them all. Check out this picture of where the part going past the narrow stretch of ocean connecting the southern Atlantic and Pacific Oceans between Antarctica and South America, called the Drake Passage, runs over. Guess which way the current flows? As you can see, the power of this current has literally shaped the continents. Well, okay, but how are we supposed to tap into that? Now look at this depth profile of the Drake Passage. As you can see, some of these currents are flowing over sections of the ocean that are miles deep. Well, okay, but how are we supposed to tap into those then? I mean, look at the tidal current power generation turbines I showed earlier. Can you imagine building a several mile high structure for these things to sit on so they can get to this power? Of course not. The key to tapping into these sources is to realize that there is a wide disparity in the current velocities between the top of the water column and the bottom. The tidal currents I was showing earlier are kind of like rivers, and they're about as deep as rivers too, with the highest flows happening around the surface. Larger currents like the Gulf Stream, the Alaska Stream, or the Antarctic Circumpolar Current don't switch directions the way the tidal currents do, and so they can build up a significant current speeds to a much greater depth. But here too, there is a massive difference between the speed of the current at the surface versus what it looks like a couple of 100 meters down. In other words, we can go down in depth a ways and hit water that moves more slowly, as in the case of large wind-driven currents like the Gulf Stream, or in some cases flowing in the other direction, as with some tidal currents. And this is one of the key ways the Seahorse will function. It will be able to get drag from lower down in the water column when it is too far from the bottom to have anchored into the seabed. Back when I was discussing the different ways of getting power from fluid flows around the natural world, I focused on a couple of current technologies, namely hydroelectric dams and wind turbines. But, of course, the practice of extracting power from natural fluid flows goes back to prehistoric times. In the Egyptian Nile, for example, almost all of the transportation needs of the civilizations that developed there were met by taking the river current downriver and sailing on the counterflowing wind current to get back upriver. And there are other examples, of course. Think about the old-fashioned windmill in Don Quixote, or this old water wheel, here in a picture from Georgia they have on Wikipedia. But over the years, the practice of using sails for transport is probably the way that we have harnessed natural currents the most in pre-modern times. Well, okay, and this is great for getting currents from wind, but wasn't this project concerned with ocean currents? Fair enough, let's talk about the ways that you can use sails underwater. Most people are probably unaware of this, but the same sails I have been discussing up on the riggings of ships actually were also used underwater during the Age of Sail. The systems I am referring to are known as sea anchors and drogues, even though they were often made of other materials such as wood instead of or as well as sails. Sea anchors are the easier of the two to understand, as they are basically an anchor that grabs still water instead of the sea bed. The first one was a picture of an early model from the Age of Sail, and here's a picture of a modern one you can find on Wikipedia. They were usually attached to the bow of the ship so that the ship would stay facing the waves that are coming in onto it. Drogues, on the other hand, are usually attached to the stern of the ship, and are smaller. They are also used by jet planes, as you can see here. Their purpose is twofold. One is more obvious, it is to slow the craft down. In the case of the jets, they are usually used on short runways. The other was important back in the Age of Sails more than it is today, and that was to act as a stabilizing influence on the ship in certain conditions. Imagine, for example, a situation in which there is a strong wind that is blowing behind a ship which is sailing into a current with waves. If the ship gets pushed by the wind into a wave like so, the bow becomes submerged, and the ship will take on a massive amount of water, compounding the problem as the ship rocks even further forward as a result. But with a drogue employed, the same ship would remain safe, because the drogue keeps the ship in a different orientation and resists any attempts to rock the ship forward. The swimming Seahorse employs both of these systems, but in the opposite ends of the ship from where they have normally been attached. So we have our ship here, and we have the sea anchor attached to the stern there, and the drogue attached to the bow there. These are some of the more complicated versions, at least. Other versions are called sedentary seahorses and are attached to the sea bed instead of getting drag with a sea anchor. I will talk about those in a little bit. Okay, so the swimming seahorse has both a sea anchor and drogue-like system. Let's start with one of them and try to imagine how a system might look somewhere in our country. Let's take Puget Sound, for example. What you see here is a tide chart for Seattle Harbor I found on tideforecast.com. As you can see, there is a big difference between high and low tides in Seattle. Here is a map of Puget Sound and the surrounding area taken from Wikipedia. As you can see, Seattle actually lies pretty far in the central basin area, meaning that all of this water is forced through areas that, while quite large, are nonetheless very narrow compared to the Pacific Ocean they come from. These are just the kind of conditions that can create big currents for us. In fact, as we go out a bit further with this map, again from Wikipedia, we can see some islands like the San Juans in Vancouver. And we can see that these islands also create narrows in the context of the Pacific, like the Juan de Fuca Strait that lies between us and the Canadians. These create big currents for us as well. As we continue north, we see that the entire northwest coast of our continent has features like this, and this entire area gets big tides, so there is huge potential here. But going back to Puget Sound, we can now see that we have an area with some big currents flowing in two different directions, depending on which part of the tidal cycle we are in. Okay, so here we have our ship again, connected to a sea anchor and drogue, only attached to the opposite end of the ship from how they would normally be set up. And the forward-facing drogue is held up higher in the water column, where we have a tidal current, and the sea anchor we are dragging behind us is held deeper, where the water is still. Check out this photograph of people paragliding that I found on Wikipedia. Looking at the article can provide some interesting info about this cool sport. Paragliders use what is called a ram air airfoil wing. As you can see from this article on airfoils, many wings, both those made by people and those made by nature, kind of fit a general template. These shapes are used because they are able to create lift as they move through the air surrounding them. Going back to the ram air airfoil used by the paraglider wing, the way that it creates lift is by having this shape formed as the wing fills up with higher pressure air from the front of the wing. This means that the airfoil it uses can be ultra-thin and light, as opposed to vehicles like airplanes, most of which have rigid wings made with sturdy internal frames wrapped in a hard shell, and often containing things like fuel as well. So this little vehicle that can be folded up into a backpack can basically act like a gliding airplane. Some people actually do make this setup into a basic airplane with a wearable motor and propeller set that you wear like a backpack, as you see here in this Wikipedia article picture. And these ultralight aircraft have some interesting flight characteristics that could be useful to us. One characteristic about the way it feels to fly in one, which it shares with a related sport like parasailing, is that they tend to feel very smooth in the air. This is because of the airfoil wing and its extremely flexible nature, the way it's able to deform to help smooth out choppy air before it ruins the pilot's ride at the other end of the cables. Other small aircraft, like this Cessna 172 that you see here from another Wikipedia article, have rigid wings that transfer much more of the unwanted effects of turbulent air pockets to their passengers. Well, like with the big currents of air that produce turbulence in the Cessna for passengers in small airplanes, tidal currents of seawater flowing through places like the Bay of Fundy are not perfectly uniform laminar flows. And this can cause a problem for turbines trying to operate in them, as it is desirable to deliver as consistent a set of conditions along the face of the turbine as possible. My hope is that the Seahorse's big underwater drogue-like systems will act kind of like the paraglider wing and absorb much of the turbulence in the surrounding current so that a relatively smooth, uniform flow of water makes it to the part of the turbine that is spinning. And having a device like the paraglider also makes it easy to steer as well. With a paraglider, the entire shape of the wing deforms and changes as a result of inputs made by the pilot by pulling on different cables. Our systems might function in a similar manner, only using an electronic winch system to pull the cables instead. If you hold your hand out of the window of your car as you drive, you can experience a similar effect as you move it around. If you hold your hand with the fingertips above your palm, it creates a high-pressure zone on your palm that lifts your hands up. If you change your hand's geometry by moving your fingers around or moving your wrist, it will change the way your hand is pushed by the wind. Holding your hand flat with your palm above your fingers will push your hand down like a sea anchor. And your hand is flexible enough to absorb the buffeting by the wind before it reaches your shoulder. In this example, your hand is actually acting a bit more like a hang glider wing in that your hand has an internal frame in your skeleton, and it doesn't fill with pressurized air like the paraglider wing or the parasailing parachute. Some of the systems that we will look at will resemble the paraglider's ram air airfoil, which we looked at first. And some more like parachutes for a parasailer, which you see here. If you are unaware, a parasail is basically a modified parachute that you pull behind something like a boat. And some will have light external frames, like with a hang glider, but all of them will share the basic idea of providing something that will use a very thin, flexible polymer sheet to create lift only underwater. Zooming out to consider the system as a whole, when the current really starts flowing, the tension will increase, and this will make the drogue and sea anchor portions want to straighten out the path between them, potentially even dragging our ship under the waterline to do so. So let's make it submersible just in case, but let's also attach it to the main cable with some flexible lines like so that it has some freedom to bob on the surface. And we'll even add a couple of lamps to it so that people can determine the craft's orientation at night. So now we have a way of getting our drogue portion and our sea anchor portion to really struggle against one another. This will create high pressure regions inside our fabric systems and regions of relatively low pressure just outside of them. We'll focus in on the drogue portion, which I also call the Seahorse's head, first. Let's make it kind of like a parasailing parachute so that it opens really wide, but we'll also make it long and filled with chambers like the paraglider's wing. Only for ours, we'll have it end in a funnel-like shape, creating a connection between the high-pressure zone in front and a low-pressure zone in the back. A current will then be formed as the high-pressure water rushes through the opening to connect with the low-pressure water behind the craft. Check out this Honeywell wind turbine, the WT6500. Unlike most large wind turbines, which feature blades that spin around a central shaft, this design has the blades mounted on the inside of a rotational ring. The way it uses this rotation is also different, as it employs a ring of permanent magnets that interact with a ring of coiled wires, more like the way many hobbyists make turbines at home. Most commercial turbines feature a gearbox that speeds up the rotation before it is used to generate power in a different kind of system. As a result of its inverted design, the Honeywell turbine is capable of generating power in much lower wind speeds than most other kinds of turbines sold today, and it is also more robust, featuring far fewer moving parts. I believe only one big ring in the bearings it rotates on, as compared to turbines with transmissions, which feature a relatively large number of moving parts. And this is another of the real keys for how this Seahorse will work. Using systems like these will allow us to take advantage of really, really slow currents compared to today's turbine designs. Not only does having the system rotate on a ring system rather than around a central shaft help with this, but the whole Seahorse system is geared towards trying to create a usable current, because the large fabric portions help to take current from the large cross-section of the flow and concentrate its power in the relatively small opening at the end of the funnel that contains the turbine itself. This is a map showing the maximum current speeds in the English Channel again. These speeds are all pretty nice, but look at where they are the highest. They are the highest in the choke point. And this will be true for our devices as well. So instead of the 2 or so knots required for most in-stream tidal turbines to function, we will be able to function in conditions where we are only getting a fraction of a knot, because our system takes the current from a large cross-sectional area of the seawater flow and concentrates it into one focused stream that runs through the turbine rings. So we will drop one of these in the back like so, and you know what, we could even add some internal fins that counter the spin on the device if we want. Or you know what, let's even add a couple more sets here and here, and that way we can spin them against each other, or we could have some combination of both. Or check out this picture of a penstock for a more conventional turbine. We could run something that looks more like this as well, but we might need to add a screen around the front, because designs like these can't just have things flowing through them the way a ring turbine might. We could also put something that looks more like the tidal stream generators you see here, only spinning inside our big funnel thing. But I think that the ring-based designs will be better solutions because they seem more robust to me, and because they can operate in lower current speeds. And again, if I am wrong about the advantages of running the permanent magnet-based solution, we could still keep the ring-based design and have it drive a gearbox like in a more traditional setup. But I think that the design I discussed first might be the easiest. The North Umpqua you see here provides water for irrigation in the summer, and I used to help people living along it with their river pumps. This river may look totally clean, but if you put anything down there during the summer months, it will get algae attached to it. I know that the screen on the intake for the pump that my parents used to run needed to be taken out and cleaned weekly, for example. So things like the screens and small openings required for the other designs might prove a pain to maintain. The ring turbine design also has the advantage of being able to allow small fish to pass directly through the center of the device. Most fish will be able to easily swim out of the turbine, but really small fish might have trouble escaping if they get caught in the current running through the device. With the center open, they can pass right through. So again, because they are low cost, have few moving parts, and because they can allow small fish to pass right through, I like the idea with the rings. But it is possible that we would want to use a different design. If we did end up needing to screen off the opening for this, we might be able to come up with a metal mesh screen made kind of like the fence that you can see in many people's backyards. We might even be able to come up with a small, cheap Roomba-like robot that could move around on one of these cyclone fence type cone screens and clean off it with a maintenance cycle. As mentioned before, we could still keep the ring design and use them to drive geared systems as well, or we could go with one of the center shafted designs. However we decide to actually try and implement the idea remains that we will connect the high and low pressure zones through a tunnel and use the resulting current to drive a turbine. But why would we want to have a turbine system on the bottom half as well? Well, one reason might be that there are currents under the water way down there too. Take the case of the Danish Straits, where there can be significant currents flowing in two different directions at once. Having multiple turbine rings that you can put into neutral when we want to will allow us to determine how much current we'll allow to flow through our devices. We might even make the blades on different turbines different shapes, so that engaging different ones would affect the amount of drag differently. This might also be useful to us in extracting power from the current in different parts of the rings. Let's imagine that we have a Seahorse in the Straits, and we want it to stay in a set area. That means that it will need to follow the tides back and forth. But if there is also a deep current that is affecting the sea anchor portion, it would be nice if we could vary the resistance so we could keep the craft on track. But the Straits into the Baltic are a weird example, with the strange flows I'm talking about being largely related to the huge amount of fresh water flowing into the Baltic from the river systems feeding it. In most situations, we could probably save money by just having a system like the one you see here, used by someone in the Navy's Leapfrog jumper team. Somewhere between a regular parachute and a paraglider wing, something like this kind of system might work well only turned upside down. On Wikipedia, it is referred to as a square ram air parachute. In fact, we could probably go even cheaper by just having a big round system like this. We wouldn't be able to steer it around as well like with the one I showed before, but is that really important? I mean, as long as we have the one on top built like the airfoil wing and can steer the system by itself, why not just use this one for drag? In fact, why not have more than one? What if we had a big stream of parachute systems down there for the Seahorse tail? This option, that of having more than one parachute system per Seahorse tail, might also prove to be a good one to have on the top as well, as it might be able to help us deal with the wave action that the head will experience. Having multiple systems in a row, like with this series drogue mentioned on Wikipedia, would also allow us to use less main cable systems. And we don't need to go with a bunch of systems that all look the same if we end up going with multiple parachutes per Seahorse tail. We could do this by having one system that looks more like the square ram air parachute that is highly steerable in front. Actually need to make it steerable, just have it constantly pull down. Though having this ability to adjust how strong it pulls down might be nice. And we could then run the big, simple sea anchor systems behind it. To understand how this will work, just think about a truck pulling a trailer. The truck provides all of the pulling power and the steering, and the trailer just gets pulled. But there isn't a problem as long as things stay in the right orientation. I even have an idea for how we could include a second different kind of turbine down here. See how there are cutouts in the shape of this round parachute so that it is steerable? What if instead of those we had slits that encouraged the system to spin? It probably wouldn't be ideal for someone jumping out of the plane, but it just might work for us. If we had a couple of them connected to a long shaft, we might even be able to get them to spin against each other, especially if the one in the back is larger to compensate for being in the wash of the other turbine's exhaust. And check out this drogue parachute being used by a jet. See how it is formed of multiple rings? What if we divided our underwater parachute system into two separate halves and then had them spin against each other? We could then attach them to a gearbox and use the spin to generate electricity like in a conventional wind turbine, or maybe we could attach the two halves through something like one of the permanent magnet rings used in the Honeywell turbine I described earlier. Why do I think that this kind of a system might work better down here? There are a few main reasons. One has to do with pressure. According to NOAA, we are surrounded by about 1 atmosphere of pressure at sea level, or about 14.5 psi. If we go down into the ocean, the amount of pressure we experience is increased by an entire atmosphere about every 10 meters, meaning that the pressure doubles at about 10 meters below the surface. If you go down a bit further under the surface, let's imagine to 200 meters, however, a 10-meter drop, while still adding another atmosphere, is not doubling the pressure. It is only raising it from 20 atmospheres to 21 atmospheres, a relatively small percentage increase. Another factor that changes with depth is water speed. Closer to the surface, there can be a significant difference in the speed of the current at different depths. So, as with the situation with pressure, as we drop through the first 10 meters of the water column, we will experience a relatively large difference in current velocity at the surface versus even just down 5 meters. Down at 200 meters, on the other hand, the water is fairly uniformly still often, so our system won't have to cope with a large difference in pressure going from the top to the bottom of the Seahorse's tail. So if we imagine a big spinning turbine up top in the drogue-like portion that forms the head of the Seahorse, we will have to worry about the system hitting more fish and other debris, which could damage the thin spinning aqua parachute we are relying on. Plus, at the top of the drogue device, we already have relatively low pressure, high speed water, and at the bottom we already have relatively high pressure, low speed water. My concern is that this difference will affect the spin of the aqua chute. That is why I like the system with the more static waterfoil type systems up top and the ones where the big fabric portions spin down lower. My thinking is that the big static systems will take the difference in water speed and pressure and even it out into one big blob of fairly uniformly high pressure seawater by the time it hits the part of the device that actually spins. Though I am sure that there will be examples where this will not be the case, I imagine that the huge variety of conditions that exist in nature will make us want to have a bunch of different options available. But the basic idea remains consistent. We will use a pair of systems, not dissimilar to drogue and sea anchor systems used in the past, that are held opposed to each other in areas where the surrounding water is moving differently. We'll create high pressure zones here and here, as well as build up low pressure zones opposed to them, and we'll build up tension in our main cable connecting the two of them. If we connect some of the paired high and low pressure zones with small holes, we can release some of this tension and we will see currents of water developed to balance out the pressure in the two zones. We can then use these currents to drive turbines that generate electrical power. The other main type of seahorse that I wanted to talk about are the sedentary seahorses. The difference is pretty basic. The first kind, the one I've been talking about, is the swimming seahorse, and it does have the sea anchor system, but it's not actually fixed to the sea floor. The second kind I'm talking about now is the sedentary seahorse, and it is actually fixed to the seabed. Remember how I mentioned earlier that the big tides in Puget Sound get even bigger as you head north towards Alaska? Well, look at the tidal amplitude map. It is made from data collected by satellites that scan the surface of the ocean from space. Just look at how big the tides get as you head up the Alaskan coast. Well, by the time that you arrive at the Cook Inlet that connects Anchorage, Alaska to the Pacific Ocean, you get to the place with the biggest tides in the U.S. Not only that, but the vast majority of the inlet is under 100 meters in depth. And just look at the size of it. The Cook Inlet is about 180 miles long. To put its size in perspective, Cook Inlet's surface area is about 20,000 square kilometers, and New Jersey is about 22,600. I love this part from the Wikipedia article on the inlet, so I'll just read it. Turnagain Arm is one of only about 60 bodies of water worldwide to exhibit a tidal bore. The bore may be more than 6 feet high and travel at 15 miles per hour on high spring tides and opposing winds. Turnagain Arm sees the largest tidal range in the United States with a mean of 30 feet, 9.2 meters, and the fourth highest in the world behind Bay of Fundy, 11.7 meters, Ungava Bay, 9.75 meters, and Bristol Channel, 9.6 meters. The ocean's natural 12-hour, 25-minute tidal cycle is close to Turnagain Arm's natural resonance frequency, which then reinforces the tide similar to water sloshing in a bathtub. Tidal fluctuations in the main body of Cook Inlet, while not as extreme as the shallow and narrow turning in arm, regularly reach 25 feet, 7.6 meters or more, and exhibit currents in excess of 5 knots. That's 9.3 kilometers per hour at full tidal flow. The inlet and its arms have been proposed as a potentially attractive site for the generation of tidal power. For situations like this, it might be nice to have a system that we can anchor into the seabed. But how could we do this in a way that keeps the systems affordable? My answer is a combination of technology from mountain climbing, technology from submersibles, and technology from well drilling. If you look around online, you can easily find videos of people drilling holes for wells, and you can also find plenty of manufacturers of well drilling systems. People have been drilling small diameter holes into the ground for tens of meters to get after groundwater for quite some time, and the technology for doing so has been made for a long time by a large number of different manufacturers. The ones you see here work by drilling down a bit with a drill bit that's a slight bit wider than the drill pipe that it's attached to. Compressed air or pressurized water is also delivered through the pipe so that the debris that is kicked up when the bit bores out the well shaft is blasted out of the way and along the sides between the pipe shaft and the hole. The drill pipe comes in big sections. Once a section being drilled down is close to the surface, another section is fitted on its top so that the drilling can continue. The ones made by the Jeep Rock Company can even be fitted with an automated system that grabs the next section of pipe from big racks and then attaches it to the previous pipe, all through remote control. That could come in handy on the bottom of the ocean because it might be nice to have an unmanned system. So my guess is that the part with the drill pipes could work pretty well for us. My one concern is with the water surrounding the drilling, which is obviously different from the air surrounding the well being drilled on the surface. But the oil industry drills into these kind of depths without any problem, so I'm sure that we'll be able to figure something out. I don't see why it still wouldn't clear with pressurized water being used. I like the idea of developing our own systems without using those developed for things like the fossil fuel industry, for the simple reason that we don't need to have a very big or deep system. Going down like 30 meters into the seabed with the narrowest drill pipe that's used for something like a water well would be fine for our purposes. And systems developed for drilling water wells are extremely affordable compared to those developed for the oil and gas industries. In a well drilling operation, after the drill pipe has finished getting down to the intended depth, it is retracted and a thin, often plastic lining pipe is installed. This pipe sometimes has thin slits cut along its length to allow for water from the aquifer to enter the system. Ours might be similar, but what if ours contained the cable inside of it? Look at this picture of a perch. Anyone who has ever gone fishing for a creature like this is aware that you can only safely handle them one way because of a series of spines that run along its body. Well, what if we had a similar system attached to our pipe? Spines attached to the cable could be made to extrude from the slits in the pipe as the cable was pulled up, thus creating a huge amount of resistance. A cool feature of a system like this could be to have the ability to later pull it back out if we use a tough reusable system, because we could simply slide the pipe the other way. As for the part of the system inspired by rock climbing equipment, another option would be to have something like this climbing cam installed at the end of the cable. With something like this, we could have a cam installed on the end of the cable, put the cable inside the pipe, and then we could have it all sunk into the position that we needed it to be in. The pipe portion would then be extracted a bit while the cable is held in position, exposing the cam. The cable would then get pulled, lodging the cam into the substrate. We could store the cable in big rolls on the deck and feed it through a cable straightener before running it through the pipes, and have them hang off the side of the ship as they are assembled. And then we could cap the whole system with a geodesic dome thing like this with a big spring in it and a BCD. My thinking is that the BCD would help us to slowly lower the system to the bottom, where we are doing the drilling, and then once at the bottom, the system would be sunk into the ground. More on that in a bit. As for the part based on submersibles, that one is probably more obvious. Check out this submersible remotely operated vehicle. We would need to incorporate features that allow systems like this to function underwater with the systems that drill the wells. If you remember back to the drill rigs I showed you a second ago, you'll recall that they're basically oriented around the need to fit on a truck's bed, because that's what carries them around. Ours, on the other hand, will need to be made to fit onto one of these things, so that's going to take some adapting. Everything will have to be waterproofed, made capable of handling the pressures they're going to experience, and we're going to have to come up with some sort of additional system that's going to keep our craft stable on the sea floor where it does the drilling. What if we incorporated a set of spider-like leg attachments? I'm thinking that the legs would start out folded up like this, then at the end of the descent to the floor, the legs would spread out like so. Once the craft gets close to the ground, scans could let the legs know where to deploy. This might let us level out the craft even on really uneven surfaces. I'm thinking that our systems would have large BCDs that would let them easily move about when getting into position. Once the drilling rig was ready, these could then dramatically reduce the craft's buoyancy, securing it to the seabed. The rig would then drill the hole and sink in the cable before moving on to the next anchor hole. The top part of the cable could be encased in a rigid steel sleeve, and there could be a huge spring connecting it to the main Seahorse cable. We could suspend it from the geodesic dome thing I mentioned earlier so that it keeps tension on the system and can't sink into the ground. Another spring on top could be used to attach the main cable. As for the tops to these sedentary Seahorses, I don't really see why they need to be all that different from the tops that I was discussing for the swimming systems. Nice. Well, now I think that we can conceptualize the main bodies for the two main types of Seahorses that I want to discuss, and I don't think that it's too much of a stretch to imagine these devices working in the water. I mean, check out these drogues that you can buy today. The systems that I'm talking about aren't really all that different from having a giant one of these things, with one of these big turbine ring things that I've been talking about to thrown in to get energy from the current flowing through the opening. By the way, remember when we started out thinking about the age of sail? Well, what if we had a ship like those from back in the day, only made of modern materials and with rigging that was worked by an automated system? We might be able to come up with a mobile Seahorse that charged it up for a while when the wind wasn't blowing, by having a system that truly wasn't much different from the drogues that I was showing earlier, but with one of the little ring turbines thrown in. Well, okay, but what are we going to do with all the power that we're generating if we're not going to use it to power a ship? Well, to answer that question, for the sedentary Seahorses is pretty easy. Just check out this tidal power turbine currently being used. It uses cables to send the power it generates back to the shore, and that's what I would recommend for the sedentary Seahorses. And I would imagine that this kind of daisy-chainable system for this might be nice. Now, what do I mean by that? Well, let's imagine that we have a section of the Cook Inlet here, and that we have some shoreline here, and that we have sedentary Seahorses where I'm drawing the little circles. Without the ability to do what I'm calling daisy chaining, we would have the situation on the left where each of the individual units send back a big cable to the mainland. But with the ability to daisy chain, seen on the right, we can reduce the distance that each of the individual units needs to be responsible for by connecting all of them together. The networks represented here are pretty small, but the advantage to daisy chaining increases with the distance from the shoreline. Doing so, we will be able to keep the distances we need to extend cables relatively short on a per unit basis. This will allow us to operate hundreds of miles from shore while having cable networks as short on a per unit basis as are used in things like wind turbine installations today. Otherwise, the longer cables required would represent a significant disadvantage for our kind of device as compared to those sorts of systems. And all that makes sense. But the question of how to get power back to the shore is a bit trickier to answer for the swimming Seahorse systems. I recommend using battery drones. But wait a minute, batteries? Won't using batteries eat into our potential for energy generation? I mean, every time that you have to move power to sets of batteries or away from sets of batteries, you lose like 15% of the available power, even with the best sets of batteries. So we would lose like 15% on both of those cycles, and then you have to add the losses that you pay to move the batteries around, plus you have to consider the fact that even really nice batteries only last a set number of charging cycles before they need to be recycled, so there's some more losses. By the time we get done paying for all of these battery losses, we might have already lost something like 50% of the power that our swimming Seahorse is generating. Will it still be worth it then, or are we stuck using these systems only in situations where we can keep them attached to the shore? Of course it'll still be worth doing. And I'll be demonstrating this by making a few observations about the competition. But before I can do that, I need you to check out these freeway overpasses. These things are big, and they are massively expensive too. Just one of these monstrosities costs as much as dozens of miles of regular roads. Made mostly of concrete reinforced with steel, these things weigh many, many tons. If we imagine cutting them into sections, we can imagine what each lane is assigned in terms of material. Now check out this gantry crane that's unloading a ship. See those cables lifting that massive shipping container? They do this all day, and those things can weigh as much as a semi-truck. Now in this situation, we have to build up the rest of the gantry crane for the cables to hang from. But if we had just the cables and their tracks and controls up on top hanging from something like a naturally formed cave that you see here, they would still be able to do the same work. So we have two systems, Both of them are used to lift similar loads, and both of them can do this all day long, but look at the massive difference in the amount of material being used to do this. The gantry crane can do this with less steel than is required for the reinforcement barring in the concrete overpass. Now take a look at this picture of Hoover Dam. Hoover Dam was constructed using a total of 3,250,000 cubic yards of concrete, according to Wikipedia at least. As far as steel goes, it includes the quantities you see listed here. Well, with that much steel, we could construct the cables for vast fleets of Seahorses. And the modern polymer constructions we will use for the fabric portions will be far easier on the environment than the millions of cubic yards of concrete used in the dam. Not to mention the fact that the most costly part of many projects like this is simply moving the soil for the project. We are talking about millions of cubic yards of rock and soil. That is a whole lot of stuff to be moved around and built for a project like Hoover Dam, and all of it has a hugely negative impact on the environment. According to Wikipedia, the cement industry is one of the global leaders in greenhouse gas emissions, and it is hard to imagine a project that is more cement intensive in its construction than a multi-million ton concrete dam. I mentioned how we could use the steel from the dam and use it to make the cables for our systems instead, and this would represent a big improvement. Remember earlier how I compared the freeway overpass to the gantry crane cables? Well, Hoover Dam is the freeway overpass in this situation, and the Seahorse is the gantry crane. We are using our material in a far more efficient manner. But I would imagine that our systems will prove even more advantageous than this, and that is because I imagine that we will be able to use modern polymers developed for the fishing industry. The use of these polymer lines will help us to save a huge amount of energy that would otherwise be required to make steel cables. But I could be wrong. I would need to have help from material scientists or some other experts like that to be sure. Either way, with steel cables or with polymer marine lines, our seahorses, swimming and anchored, will use the material required to make them in a more efficient manner than concrete dams or wind turbines. And this more efficient use of material is key because we are going to be blocking a huge amount of water with these things, which is important for us because we aren't going to be able to develop as much pressure as a big dam. Remember earlier how I explained that we will be using the big parachute or airfoil wing-like parts of the Seahorse to develop a large amount of pressure on one side of them, and that we're going to generate current by connecting these pockets with the relatively low pressure water on the other side? Well, dams like Hoover Dam do the same thing, only they're able to develop a much larger difference in pressure. So the current connecting the two zones is far more powerful than the one connecting the zones around our Seahorses. And this would be a problem for us if it weren't for the fact that the Colorado River is actually not all that big. In fact, no river is all that big compared to the Amazon, which is bigger than all of the others combined. And remember that tidal currents that go through the Bay of Fundy alone are much larger than the flows through the entire Amazon River. So all of that investment that I described earlier for Hoover Dam is to block up the flow of just one tiny stream. The rates of discharge for rivers are highly variable, but to put it in some kind of perspective, the Colorado has a maximum discharge of about 1/30th of the maximum discharge of the Amazon. As you can see, the average flow of the Colorado is far, far below this maximum discharge. So even on the most powerful day in the river's history, it boasted just a tiny fraction of the flow that goes through the Bay of Fundy every 12 hours. I have plans for systems that function in rivers like the Colorado too. When many people see a river flowing free from one end to the other, undammed for its whole extent, many of them think that it's flowing quote-unquote naturally, but this is not the case. In fact, if we were able to go back to the time before the ancestors of the Native Americans were supposed to have first crossed over the Bering Land Bridge, we would find a continent full of dams, far more dams than there are to be found here today, in fact. State animal to my home state of Oregon and national animal to Canada, the North American beaver once had an enormous impact on the hydrography and through it the geography of the United States. Though the Native Americans used the beaver as food and a source for pelts, these creatures still had an enormous presence in this continent up until Columbian contact and then for a little bit after that as well. When I say their impact was enormous, I mean it. We must remember that the Native Americans practiced very little logging compared to contemporary European civilizations. As a result of this fact, there were large forests growing along the shores of most of the rivers throughout the continent. This meant that there was always dead logs and growing trees in abundance. As a result of the activity of beavers and the impact of just having so many logs in the water naturally, log jams could develop that would block up major rivers for nearly 100 miles and for many years. And of course, beaver dams create beaver ponds, and giant log jams block up even more water, which dramatically increase the amount of surface water sitting around. And this is why we can't really have the beavers just come back into areas where we have lots of people today. Rivers are powerful natural forces, and by manipulating them and their flows, beavers can create massive and massively expensive problems. Most communities just aren't okay with a group of giant rodents deciding what large acreages of riverfront property should be flooded on a random year, despite the wishes of the people living there. But our decision to control the beaver population isn't such a great choice for the rest of the animals or the plants involved, because beaver dams were actually beneficial to the ecosystem. This is in contrast to dams like Hoover Dam, which are seen as almost entirely damaging to the river's ecology. The beaver dams would slow the flow of streams rather than stopping them entirely. This caused the rivers to swell as they required much more time to empty. And this in turn caused the water to get colder. Check out this picture of the Colorado River. See how it is brown and full of sediment? When sunlight hits this water, it is only able to penetrate so far before it is absorbed by the effluent in the stream. So any extra water adding depth to the stream is shaded by this section of warm water on top of the river. And so this is how, by slowing the water down, the beaver cooled it. This keep more water in the river because cooler water doesn't evaporate as much on hot days, so therefore it created sort of a virtuous cycle. It also allowed more water to stay underground. Many people don't realize this, but rivers are largely fed by groundwater. Think about the way a well works, and you'll get how a river fills up this way. Well, a higher river water pulls less water from the surrounding groundwater reservoirs, allowing them to build up reserves for time of drought, as opposed to a lower river level, which will act as though you're drawing from a bunch of wells. Anyway, to make a long story short, I have these things called beaver dams that are similar to the seahorses that people can use to dam up rivers in a way that is more reminiscent of the way the beavers used to operate, while still producing manageable flows that generate power. I will be talking about these in their own dedicated movie at some later time. The reason I bring them up here is just to point out that if you want to imagine them in a river like the Colorado, it's important to remember that they are repeatedly damming the same river. Now, dam for dam, these beaver dams are not going to generate as much power as Hoover Dam, but this is balanced out by the fact that you get the added effect of many dams. So even though they are far weaker, by the time you have hundreds or maybe even thousands of beaver dams, you start to be able to compete with something like Hoover Dam, and you do so in a way that is actually beneficial to the native flora and fauna rather than harmful, and in a way that creates lots and lots of jobs on a continuing basis, getting us back to conditions more reminiscent of pre-Columbian contact with the ecology in the process. And the same will be true for the massive streams that are these oceanic tidal currents. We will be able to tap into the same current flows over and over on the way to the terminus of whatever body the tide water is heading towards. So the flows are much larger, and we are able to tap into them many times in a way that has minimal impact on surrounding wildlife. Okay, so I have made some arguments for why I believe the Seahorse systems will perform well against conventional dams. Well, how about against the wind turbines? I mean, sure, there are bigger flows of ocean water out there than there are rivers, but what about wind? I mean, it isn't even close volume-wise, and the atmosphere is constantly being whipped around at speeds that are much higher than you can get for currents in the ocean. I mean, just look how big wind turbines have become. Imagine the area of the circle that is made by the tips of the blades revolving around. Pretty massive. How is it that I hope to compete with this? Well, check out this parachute that's slowing down this cargo crate. It's getting power from a huge section of air too, and it's getting it from something that can fit into a backpack. This parachute is actually getting a huge amount of power to slow the crate, an amount comparable to that of a big wind turbine. It's just not in the form of electrical current, so a lot of people don't recognize it. You could probably fit hundreds of parachute packs just in the middle part of the big turbine you see depicted here, and God only knows how many in each of its massive blades. Of course, the cargo parachute is only good for slowing down freight as it falls, whereas the wind turbine generates electrical power that can be used in a wide variety of applications. But, of course, the Seahorse is capable of generating electrical power in a similar fashion. So I'm going to claim that, like the cargo parachute, the Seahorse actually uses the material it is made of far more efficiently than the wind turbine competition. This comparison of wind turbines and backpack-sized parachutes is, of course, similar to the argument I made with a gantry crane in the freeway overpass earlier. It is interesting, I think, that it is natural for people to think about building things up when they invent stuff. There's something that just seems more natural to inventors about building up a big rigid structure in the middle of a flow and having it stand there defying the current. I think that these structures might represent something to these people. But there's actually something about these devices that use tension. They're really incredible. Just look at these spiders' webs. Such strength and utility, and yet they're just such tiny things. But walk through one, and you, a creature many orders of magnitude larger than the spider, can feel it restraining you a bit. I don't have the technical language to express why it is, but I'm telling you that the forces binding together the steel in cables or the strands in polymer marine lines are incredibly powerful for their size. When it comes to strength, devices optimized to take advantage of tension, be they winches, spider webs, gantry cranes, or parachutes, punch way above their weight compared to devices made to support similar loads by building up rigid structures. And so I'm starting this comparison with a wind turbine with a similar argument as I used to begin my comparison against a concrete dam. The Seahorse uses material more efficiently than the turbine does. And my second claim is the same as that made against the concrete dams too. The Seahorse will be able to tap into bigger flows. But volume-wise, the flows of air in the form of wind in the atmosphere are much, much larger than the volume of water in the ocean flows, right? Well, sure, but we also have to remember that the wind turbine competition we're up against is only able to get to wind that's within range of its tallest turbines. Realistically, I imagine that the kinds of systems that we will be making to get power from ocean currents will have parachute systems that are every bit as big in diameter as a circle made by the path swept out by the tips of a big wind turbine. So system for system, we'll be getting about the same cross-sectional areas of flow. Now, the flows of wind tend to be about a degree of magnitude faster than the speed of the flows in the ocean. And not only that, but kinetic energy goes up as a square of any increase in velocity. So the wind speeds that are 10 times faster than the speeds of ocean currents actually carry 10 squared or 100 times the more amount of kinetic energy than they would if they were going the same speed as the ocean currents. And that would be a problem for us if it wasn't for the fact that seawater is about 1,000 times, or 3 orders of magnitude, more dense than air is. So even though increases in mass only have a linear relationship with increases in kinetic energy available for us to tap into, the seawater flows still end up with about 10 times the amount of available power, or about 1 order of magnitude. And the situation gets even better for us, because look at this wind turbine. We've been talking about the circle swept out by its blades, right? But just look how little of that circle is actually covered by the blades. Most of the current just passes right by. But our Seahorses, looking more like these systems, won't have this issue. Almost all of the cross-sectional area is covered. And even though each individual turbine ring allows current to pass through, in the end, they each end up getting a section of it, so a large percentage of the energy available in the flow does get eaten up because we can use multiple rings. So the saltwater flows that the Seahorse taps into are slower, but they are so much denser that they contain more energy for us to tap into. Not only that, but we will be able to tap into a bigger percentage of the flows that we end up working because our systems don't just allow a vast majority of the current in the cross-section they cover to pass right by. And last but not least, the Seahorse will accomplish all of this while using just a tiny fraction of the material that is required to build up one of today's big wind turbines. Man, that was a long digression. And so, to go back to the main narrative, yes, it will still be worth it to build the swimming Seahorse systems. Even with the use of batteries potentially eating into half of the power that we're getting, because they are so much better than the alternatives, it will still be worth building these things. I'm thinking that each individual Seahorse unit will have multiple battery units and that these batteries could get swapped out by automated systems. As for what the battery swapping craft could look like, we want it to be able to handle rough weather, and we also wanted to be able to have a very fuel-efficient system. It would be nice to have a system that could carry a couple of crew members if they needed to perform maintenance on the Seahorse or something too. The boats for the battery swapping systems could be built with an extendable arm or something that grabs onto the side of the Seahorse's boat and brings it alongside. Once it's secure, the automated system could then swap out the charged batteries from the Seahorse with empty ones that it brings. I'm replaying this footage of the automated rod handling system from the Deep Rock Company to demonstrate how this might work. If an automated system like this can handle massive metal drill rods several meters long and drill water wells for tens of thousands of dollars, I'm sure we can come up with an automated battery swapping system for the same amount of money or less. Remember earlier how I tried to shorten the cable network for our sedentary Seahorse systems by daisy chaining them? Well, we will try and do a similar thing for the battery drones. Where they're near land, they can reach automated docking stations installed at the shore that will let them drain their systems onto the grid. If the Seahorses are operating far from land, however, we will have to install a limited network of undersea cables. These will have floating battery stations installed to reach the surface of the ocean in areas too far from the land for the battery ships, so that the battery drones can drain their systems into them. One concern that I have with this idea is that bad weather could make docking the systems together on the ocean surface very difficult. It is possible that a better idea might be to have a system like the one that I've been describing, only with the batteries being placed on small submarines, and having the larger battery drones carry a submersible as well. That way, the battery drone would approach the Seahorse on the surface before sending a submersible drone below the waves as it got close by. The Seahorse would send out some full batteries and receive some empty ones, all while underwater in an exchange between two submersibles where the waves and weather can barely be noticed. After the exchange, the battery drone submersible might interface with an electromagnetic system hanging in the water. The drone would become attached to the magnet, get pulled out of the water, and be placed on the deck, after which the magnet would be switched off. Having a submersible battery drone could also make draining the battery systems onto the grid with the mid-ocean docking stations safer, as we could have them held underwater. Take a look at these diving bells. If we do end up using underwater docking stations, they might have a section with a diving bell that lets us connect the sub to a dock in a water-free environment. And there are other options besides batteries. One option that I've considered is using a liquid salt heating system like the one developed by Solar Reserve. Their technology allows you to store energy in the form of heat, which is absorbed by a liquid salt that maintains a workable viscosity through a huge temperature range. This stored thermal energy is then used to operate turbines before it cools and needs to be heated again at a later time. Well, we could have a similar system with our Seahorses heating the salt on site and sending submarines of superheated salts that could be used to generate steam for turbines feeding energy onto the grid. Check out these thermoses for sale online. These things feature a relatively hard vacuum and allow very little heat to escape. Long beefed up versions of these, especially if we use a couple of them, one inside of the other, might work as tanks for liquid salt submarines that could go back and forth without losing much thermal energy at all. No matter how we do it, I think that we can certainly come up with a system that is a far cry better than how fossil fuels are shipped today. Take a look at the Deepwater Horizon Gulf oil spill, or Exxon Valdez, to see what I mean. Currently, we have offshore oil operations in far-flung places like northern Alaska. These sites pump oil out of the ocean, and then they send it to where it needs to go. If it needs to go to Asia, it might be put onto tankers and then sent all the way across the Pacific. Distances like these make the distances our liquid salt or battery drones servicing our swimming Seahorses will have to go seem insignificant. And even if the oil is just getting sent to us south of there in North America, we're still talking about thousands of miles. And it can't go all that way in a pipeline. Eventually it will need to get pumped onto tankers and driven all over to the different gas stations, and all of this wastes energy and has the potential for environmental devastation should a spill occur. Our Seahorse systems, on the other hand, rely on the transmission of power as electrical current for the vast majority of the distances they send power across. What I'm trying to point out here is that while our swimming Seahorse systems will have to have automated salt tankers or battery subs in order to operate, these systems will still represent a significant advantage over current standards. These subs will operate very safely and will be retrievable should anything happen to them. Alright, so now we have some idea of how both our swimming and our sedentary Seahorses will operate in the ocean to generate power when the tidal currents are flowing, and how we might get that power to the grid. But what I've left out thus far is an explanation of how they will get into position to be able to get the currents once they're flowing. Here I have a tide chart for Seattle again. The areas where the tide chart has the biggest slopes represent the periods when we'll have the biggest currents to work with. But the periods where the slope is zero, the peaks and valleys of the modified sine curve thing that is the tide chart, represent the periods when there's a lull in the currents before they begin flowing back the other way. So let's imagine a swimming Seahorse over one of the deeper parts of Puget Sound during this period. Without the current flowing, the system doesn't have tension to keep it in shape. In the best case scenario, it would just kind of hang there, but if there was any other currents around, it could move all over. And then when the current begins flowing the other way, the system will get hit with it in the wrong orientation. The big parachute parts will get dragged along, twisted up in the connecting cables until the whole thing is a complete mess. And a similar problem will happen with the sedentary Seahorses. What we really need is a way of swinging the systems around so they're ready for the changing current. And that's where HiveMind comes in. HiveMind is what I call a system that's going to help us solve this problem. So how does HiveMind work? Well, think about a navigation system that you're familiar with. If you have a Garmin, you've used a car company's navigation system, or you've used an app like Apple Maps or Google Maps on your phone, you'll have a pretty good idea of what I'm talking about. Let's take the big two, Apple Maps and Google Maps. With either of these mapping apps, we are able to put in a destination, and then the app will use our device's GPS, along with accelerometers and other sensors, to determine your position and orientation. Using this information, the app then checks things like road maps, traffic alerts, weather info, past traffic patterns, and info about planned road construction projects and detours, to name a few, to produce instructions on how to get to your destination as quickly as possible. Well, now I want you to imagine that there are roads in the ocean that we can just draw in, as though they were the real thing for our system called HiveMind. Okay, well, our HiveMind system won't just use our phone's GPS, accelerometers, etc. to tell us where to go. It will actually control our seahorses and make them actually go there in reality, a step beyond what these navigation apps do currently. Well, now I want you to imagine that there are roads in the ocean that we can just draw in, as though they were the real thing for our system called HiveMind. Okay, well, our HiveMind system won't just use our phone's GPS, accelerometers, etc. to tell us where to go. It will actually control our seahorses and make them actually go there in reality, a step beyond what these navigation apps do currently. Well, we would need to set the BCD, or buoyancy control devices, on the craft. If you don't know what these are, check out this picture from Wikipedia. That thick vest is a BCD. If an underwater diver wearing one wants to go up, they hit a button and compressed air from the tank enters the vest, increasing its volume without the diver having to take on any additional mass. If they want to go down, they can vent some air from the vest into the ocean, reducing their buoyancy. Submersible drones like this one have systems that do the same thing. So the HiveMind software will need to control the drone's BCDs in order to get to the right depth under the waves. As for how to move around laterally, look at the unmanned submersibles you see here. They all use a combination of fins and propellers, so HiveMind must be able to control these as well. And that's about all we should need. Now, if we can have HiveMind control how deep it goes, how fast it goes, and in which direction, within the craft's capabilities, of course, we should be getting ready to go. So let's go back to our map of Puget Sound with the quote-unquote sea road drawn in. Now, as long as we can get a signal to our submersible and keep it charged up, we should be able to keep it going back and forth on its course. Well, okay, so then if we add the right size propellers, motors, BCDs, and a GPS unit, accelerometers, and other sensors, the way we did to the other submersible, and something like a smart device to operate it all, our Seahorse systems should be able to do the same thing, right? We might be able to add a rigid fiberglass collar to the front opening of our systems that would let us mount a pair of big fins and some propellers as well. And let's imagine that the tube in the back with the turbines in it is made of fiberglass as well, and that we mount additional propellers and fins on it. Now we can commute up and down on its sea road with its propeller and fin systems. And to be clear, if we go back to the quote-unquote sea road in Puget Sound from before, we'll not be responsible for powering most of the motion back and forth on this path. Ideally, we would only have the device move a few inches if we could. It only goes back and forth this far because the sound is too deep in some parts to have an anchored system, and so we have to make do with the sea anchors. All we really have to power are a pair of turns at the ends of the Seahorse's paths, where it needs to change direction with the changing tides. I am thinking that we might want to drop the bottom of the system down and then spin it in a 180-degree turn. That way, when the current begins flowing in the other direction, everything's ready to go and we'll use minimal energy. We won't really need very big or powerful systems to handle this. Another thought I had is that we might take some inspiration from these parasols or umbrellas. This kind of a system would be a bit different from most umbrellas in that it would still rely on tension for dealing with the current. The light frame around it would only be to keep the shape of the device when it was going through the turn. We might even be able to come up with the systems that can fold down to reduce drag during the turning maneuver before reopening to meet the current as it begins to flow in the other direction. Such designs might make it easier to drag the system with towboats also if they ever need assistance moving through the water. And in that way, they would be more like umbrellas. So, in that way, let's put a light metal frame that connects the collar in the front of the craft to the turbine in the back. This system isn't there to hold the parachute taut or anything like that. It's simply there to keep the basic shape of the craft. when it isn't being filled with high pressure water from the current that keeps it taut. But there could also be advantages to having a frame that provides some support while the system's generating power, as I mentioned earlier, when I went over how the system could function more like a hang glider. In these setups, the fins, propellers, and turbines help to control the Seahorse as the systems are riding the tidal currents. The big fins will allow us to change directions. The turbine rings and the propellers around the outside of the craft will help us determine how much resistance to the flow we present. With the simpler systems I described earlier, we might come up with Seahorses that are mainly controlled by little winches that pull on cables to change the shape of the craft they hold. In the turns, there might just be a team of 3 little submersibles that pull the fabric taut and hang the system almost vertically before spinning it and partially reopening it to meet the oncoming current, more like the paraglider controls from earlier. Going back to the example with the added propellers, though, think about an electric car with regenerative braking. When you want to go forward, you use energy from the battery to accelerate, and then when you want to slow down, the car's regenerative braking system is able to take the car's kinetic energy and reconvert it to electrical energy that can go back to recharge the batteries, at least a little bit. Well, the propellers we add to the outside of the craft will work like this too. When we need to turn the craft around, we will need to power the propellers with battery power. But when the craft is riding the tidal current, these can be run in reverse, kind of like the regenerative brakes on an electric car, so that the spin induced by the blades while the current goes by can go back to charging the system's batteries. And we might be able to design our main power generating turbines with variable resistance as well, which would provide us with even greater ability to control the speed of the craft as it goes back and forth. And so we'll be able to control how much resistance is offered this way, like you control the resistance the brakes in your car offer. And this will allow us to keep the systems on track as they're harnessing energy from the tidal currents. Okay, and now I think we can imagine how these things might go one way, turn in 180 degrees, and then head back the other direction. The reason that I call these systems that controls these things hive mind is that it controls all of these systems at once. So it can get info from all the different constituent systems in return. Hive mind will constantly be getting info about changing conditions from a huge number of Seahorses, and it'll be learning about the environment more and more over time and adapting to it. It'll be able to listen to the different systems, to be able to associate different sounds with different problems, and it'll just get better as the system evolves over time. Another thing that I kind of worry about is the action of the waves. Remember earlier, Roland and I mentioned that the system will ride the waves? Well, I worry sometimes that the top half of the system is going to do this a little bit better than the bottom half. And this might stress the system out when the wave is rising and then relax it when the wave goes back down. Now, these devices will operate in deep water where massive waves are typically not such a problem as they are close to shore, and if there is ever any great danger, we can always just sink the system under the wave action until the storm subsides. I mean, what if we just had a system that would open up the Seahorse's head drogue-like system, allow it to get dragged by the current for a bit, spin up the yo-yo thing, and then once it's reached its maximum length, collapse the drogue-like portion before quickly resetting the system to begin another cycle by hauling the collapsed head portion back into position. In this way, we could have lots of wade and tidal current power without having a big spinning turbine exposed to the marine environment. Who knows, maybe eventually we can control the systems to such a large degree where we can actually organize and to some extent shape the waves around our system by controlling huge Seahorse herds. This could be especially useful in a place like the Drake Passage where the weather tends to be absolutely terrible. What if we could control a huge line of systems that would all keep the wave action somewhat subdued? Could this create a safe shipping lane that could be used by other traffic as well? Or could we work to make certain waves extra big so they'd catch more wind? Who knows? Speaking of the cables, check out this decoration. See how it's highly visible, but it doesn't have much material to it? What if we had something similar around our cables? Then we might be able to have a string of little LEDs like these, or maybe even little speakers so that we could flash the lights or make snapping noises. I wonder if we could keep the lights dim, something like might be produced by something like bioluminescence, and we could keep the snaps faint, like something that different sea creatures might be heard, if we could include that without bothering other marine life too much. My idea here is basically to have something that's going to alert megafauna, so big guys like sharks or rays or whales, that the system's there before they'd otherwise possibly run into it at night. Because that's one of the only concerns I have when it comes to possible negative impacts to the local flora and fauna. But if you think about something like bull kelp, I know that this stuff grows all over and that those big megafauna critters I was talking about can definitely get around that, so it probably won't be a huge issue for them. Perhaps we could get a sort of cheap automated sonar or something that could detect incoming wells and et cetera from 100 meters out or so, and only begin the flashing and snapping if it was going to pass within a 50-meter radius or something. And that's just about it for a basic rundown of the way I conceptualize a seahorse. I really don't know how these things would end up looking in the real world. I can think of a bunch of different directions to take the basic idea and tweak it a bit. Fiberglass is very cheap and strong, for example. Having a more rigid system made out of big fiberglass sections might make the turns easier. Or what about a part rigid fiberglass, part flexible fabric hybrid? So there's many examples of rabbit holes to get lost down on a project like this. What exact kind of battery, what exact type of turbine setup, how big the system should look. These are all important considerations that we'd have to go over. I'm not going to do that here, but these are the sorts of things that we would have to figure out for the Seahorse to truly come to be. Yeah, and as for how it could actually become a reality, I would love to partner with a university in an English-speaking country to work on it. I love the Seahorse idea. It's one of my favorite daydreams, and I want to see it help save the environment. I'm convinced that this won't happen necessarily if it's developed by the private sector. I don't want it to be used in a way that overly stresses the environment, and I think that a university might see things the same way. I don't want them to be manufactured in sweatshops or somewhere, and I think a university would see things the same way there too. And look again at this tidal amplitude map. I mean, there's lots of places in the Anglophone world to choose from where there's huge public assets. And this whole Seahorse idea is, after all, just a daydream. I'm thinking about making a series called Documentary of Daydreams, and this is, one of the installations. So I don't have a degree in engineering or any other real qualifications to come up with something like this, particularly on this scale. So maybe there truly is a good reason why this idea could never work, but I honestly don't know what it could be, and that's why the idea really bothers me. I haven't made anything up about the actual situation with the tides. There are huge areas like the Cook Inlet and the English Channel, just to name a couple, where you can find massive tidal currents moving huge amounts of seawater in sustained flows for over 1 knot for long periods, like we're talking hours. And almost nothing is being done to try to tap into this power, while enormous investments are being made in things like wind turbines and solar panels that are after things that don't have the energy density that we could get at here. And don't get me wrong, I think that other green technologies like the ones I've been mentioning are great. I just think they're lower priority. And it seems to me that exploring the potential that the Seahorse has to offer is also a good idea. If I had it my way, we'd develop the basic systems at a university, like I said, and then we'd test them out. And only once we had a really good idea of how these would affect the surrounding flora and fauna and other man-made marine traffic would we then consider exploiting the actual tidal flows for real. And even at that point, I would love to see about half the jobs in the industry stay with the schools. How cool would it be if we could have half of one of our big energy industries controlled by a large institution that was run by a bunch of idealistic young people and intellectuals? I'm telling you, our planet is super special. In all of the inner solar system, we have by far the largest moon of all. The only ones that are comparable are way out by the big giant planets, and it's ridiculously close to us, this moon of ours. And I mean, honestly, it's a completely unique situation. There's nothing else like it in our entire system. This heavenly companion of ours drags along with it, in cooperation with the sun, a huge tidal swell of water all across the global ocean. And it is gigantic. Look again at this tidal amplitude map and think of the magnitude of what I'm talking about. And what are we doing to tap into this immensely powerful phenomenon? Almost nothing. Well, the Seahorse can change that. The Seahorse has the potential to extract power from the tides and much, much more. From the Alaska Current running up to our biggest state, to the Gulf Stream running along the eastern seaboard, to the granddaddy of them all, the Antarctic Circumpolar Current, our oceans feature some truly colossal flows that have hardly been tapped into at all. Thank you so much for taking the time to watch this movie. Now, let's get out there and get this power.